So previously I mentioned that I was going to prove that Fn forms a vector space, but instead I'm going to prove that f of r forms a vector space. Now, if we need to recall what f of r is. F of r is the real valued functions. So it's the set of f, the set of functions that map the real numbers to the real numbers. Okay? Now, with this set of functions, we have to talk about how we add functions. So we need addition, which maps f of r cross f of r to f of r. And we need multiplication. Now, multiplication is going to take r cross f of r and map it to f of r. These are the two operators, but we need to define them. And here's how we define them. F plus g of x is defined to be equal to f of x plus g of x. And cf of x is defined to be equal to c times f of x. And this is true for all x in R. Now, this might feel a little strange. Why is this f plus g and f plus g? What's going on here? Well, let's try to think back to grade 1 or 2 when we first learned functions. Some of you may have seen this picture here, okay? Where you have some sort of machine. You have your x values, and here is your f of x values, and this box here is f. And let's say I have a function like this. And I have g of x. This is g and this is x. Well, what this is saying is this definition of addition is saying that if I take these two numbers and I add them together, and I look at the machine f plus g, my input's x, this is my output. My output is these are going to be equal. This will be f plus g of x. And it's defined to be equal to the output of the f function plus the output of the g function. And that's how we define the addition of functions. Okay. Now, to prove the axioms of the vector space, well, we have a similar breakdown to what we had before in our field. We have two closure statements. We have a 1, 2, 3, 4, 5, 6 left side equals right side statements. And we have two existence statements. Right? So to prove this forms a vector space, we have to show it satisfies closure. We have to show that it satisfies left side equals right side for these 6 statements. And we have to show that there exists our zero vector and there exists our additive inverse. So we're going to start with our first closure statement. And the first statement is that our plus operator maps f of r cross f of r to f of r, or our real valued functions. Now, how do we prove this? We prove this by showing that for all x, or for all f and g in f of r, f plus g is in f of r. Now, what does it mean to be in f of r? Well, f of r is, as defined above, it's the set of functions which maps r to r. Well, what does it mean to be a function that maps r to r? Well, f is in f of r. This means, or if and only if, for all x in r, f of x is in R. So what we need to do is we need we need to show that if both my functions f and g satisfy that that all real numbers have an output that's a real number, then the function f plus g takes in all inputs and outputs all inputs. So we want to show, we want to let f and g be in f and R, and we want to show that f plus g is in f and R. So let's go through the proof. We start with f and g is in f of R. So let f and g be in f of R. Then I like to follow up with what this means. That means that for all x in R, f of x is in R, and g of x is in R. And what do I want to show? I want to show that for all x in R, f plus g is in of x is in R. Okay. So to show that for all x in R, f plus g of x is in R, I'm going to consider or let x be in R. I'm going to consider a generic element x, and now I'm going to consider f plus g of x. So this is f plus g applied to x. F plus g applied to x. At this point, I don't know anything about the function. The only thing I have is the definition of addition. But the definition of addition allows me to get f of x plus g of x. And this is by definition of addition. Next, I want to show that whatever this is, it's in R. Well, I know because f and g are in f of R, that f of x is in R and g of x is in R. So to make this a little clear, I'm going to say let a equal f of x and b equal g of x as f and g are in the set of real valued functions, a and b are in R. Thus, f of x, or sorry, f plus g of x, which equals a plus b, is in R as, erase those, as addition of real numbers is closed. This means that the output of f of x, f plus g of x, is in R. Okay? Thus, f plus g is a real valued function. Why is it a real valued function? I've just shown that for all inputs into the function f plus g, the output is a real number. We are now going to prove axiom 3. And in axiom 3, we are asked to show the existence of a zero vector or a zero element. So we need to come up with a zero element. But remember, our set V is the set of functions. So we need to come up with a zero function. Now, what we're going to do is we're just going to consider a function. We're going to consider, and I'm going to put a little arrow on top because it's hard to bold, the zero function in the set of real valued functions. Now, I have this zero function, but I got to define it as a function somehow. Well, I'm going to define it such that 0 of x equals 0
for all x. And this here is the number 0, whereas this is the function 0. Okay. What do I want to show? I want to show that 0 plus x equals x. Okay. Now, how do I show that 0 plus x equals x for all x in x? Well, x here is a function. So I want to show that 0 plus f equals f for all f in the set of real valued functions. Well, how do I show that two functions are equal? I've got a function on the left side and a function on the right side. I want to show that they're equal. Well, this means to show that two functions are equal, I want to show that 0 bar plus f of x equals f of x for all x in R, because that's how we show two functions are equal. Okay, so this is what I want to show. I want to show that this is true. And if I can show that this is true, I've shown that the 0 function acts like the 0 vector. So this is my goal. Okay, we'll take this and we'll move it all over here as the thing I want to show. And we'll carry on with the proof. Okay? It's often helpful to figure out what you want to show before you dive into the details. So now, because I want to show that this is true for all x, I'm going to do this by saying, let x be in R. Consider and f be in f of R. Now I have a general function and a general x. Okay? So it's a general x and it's a general function. Now I'm going to consider 0 plus f of x. Now 0 plus f of x, this equals 0 bar of x plus f of x by definition of addition, which equals, now 0 of x equals 0 plus f of x by definition of 0r. And now this here, this is the 0 number, and this is also a real number. So this equals f of x, as 0 is the additive identity of R. So what I've shown is I've shown that 0 plus f of x equals f of x. As x was general, 0 bar plus f equals f. Thus, 0 acts as the additive identity, i.e., it exists. And we've proven the existence of the 0 vector. It is the function that when you plug in any x, you get 0. We're now going to prove one of our left side equals right side axioms, specifically A1, associative. And to be associative, this means that for f, g, and h in the set of real valued functions, f plus g plus h is equal to f plus g plus h. Now, this is our goal. This is what we want to show. Now, how do we show this? Well, what we're going to do is we're going to consider a generic function and show these generic three functions and show that these are equal to each other. And now, how do we show that two functions are equal to each other? Well, f equals g if for all x, f of x equals f of, or g of x. So we need to show that for a generic input, the outputs are the same. That means I need to not only consider generic functions, I then need to consider a generic input. So consider, or let's let f, g, and h be real valued functions. Now, let x be a real number. We want to show that left side equals right side. So we're going to start with consider f plus g plus h of x. So the left side, let's apply this function to x. Well, how would I compute this? This would equal f of x plus g plus h of x by the definition of addition. Okay? And this would equal f of x plus g of x plus h of x by the definition of addition. And this is our function addition. Okay? Well, now we can see the other function. The brackets are in the other order. They're not bracketing the second two, they're bracketing the first two. If we look here, these are the outputs of the real valued functions, which means they're real numbers. And so I'm just simply adding three real numbers. And that is an associative operator. So this is equal to f of x plus g of x, all plus h of x, as real addition is associative. And now it's kind of like working backwards. We're going to try to get now to this function applied to x. So I'm going to undo this definition of addition to get f plus g of x plus h of x by the definition of addition. This, now I have a function of x plus another function applied to x, which equals f plus g plus h, all applied to x by definition of addition. And now if we look at it, this is my left function of x, and it's equal to my right function of x. Thus, f plus g plus h equals f plus g all plus h, as the outputs are all equal. And this is the approach that we would take to prove left side equals right side.